Welcome back everyone. Today we learn about periodic table. The areas we will be focusing on are Group 1 alkali metal, Group 7 halogens, Group 0 noble gases and lastly, transition metals. As seen in the diagram below, it shows what type of elements belong in each group. The black line drawn in the diagram below is known as the metal and non-metal line, where it separates the non-metal and metals. As seen in the diagram, the metals include Group 1, 2, transition metals and those of Group 3, 4, 5, and 6 that are not shaded. On the other hand, the non-metals will include those of Group 7 and 0, while also those of Group 3, 4, 5, and 6 that are shaded. Atomic size. As seen in this diagram, across the rows, atomic size decreases, while down the columns, the atomic size increases. As indicated by the red arrow, the horizontal rows of the periodic table are called periods. Elements in a period have the same number of electron shells. However, they do not share similar chemical property and do not share similar physical property. When focusing on period 3 elements, we can see that while they all belong to the same period, sodium, magnesium, and aluminium are metals, while silicon is a macromolecule, and lastly phosphorus, sulfur, chlorine, and argon are covalent elements. When looking at the boiling points of period 3 elements, the metals and macromolecules have high boiling and melting points, while covalent elements have low melting and boiling point. On the other hand, when looking at conductivity of these elements, the metals are good conductors while macromolecules and covalent elements are poor conductors of electricity. Now we shall focus on the oxides of period 3 elements, and you can see the different oxides of each element, with sodium and magnesium forming basic oxides, aluminium forming the only amphoteric oxide, with the rest of the elements forming acidic oxides. Similarly, the oxides of sodium, magnesium, and aluminium form ionic compounds, while silicon forms an oxide that is a macromolecule, and the rest of the elements form oxides that are covalent compounds. The ionic compounds and macromolecules that are formed have high melting and boiling point, while the covalent compounds formed have a low melting and boiling point. The red arrow points to a column, which is known as a group, and elements in any group will have similar chemical properties. Elements in a group have the same number of outermost electrons, they undertake chemical reactions in the same manner, and share similar chemical and physical properties. As seen below, the compounds below which have cations belonging to the same group are similar. Group 1 alkali metal. Alkali metals reacts with water to form alkali. They can be cut by a knife, are highly reactive metals, form metallic bonds, and are silvery and shiny, while being able to conduct electricity. Alkali metals also have a low density, and all the group 1 salts are soluble in water. Down the group, there is a decreasing melting point, increasing reactivity, and increasing density. Down the group, the relative molecular mass increases, and since density is equals to mass over volume, the density will increase. Down the group, the atomic radius of group 1 elements increase, and it is easier for elements to lose electrons, and therefore elements are more reactive, as seen in the diagram below. The melting point is synonymous with the strength of the metallic bond, and down the group, the atomic radius is larger, and for the same number of delocalized electrons, weaker metallic bonds are formed. In summary, down the group, there is a decreasing melting point, as with the same number of delocalized electrons and larger ions, weaker metallic bonds are formed. There is also increasing reactivity as the atomic radius increases, thus making it easier to lose electrons. And lastly, the density increases as the mass number increases. Alkali metals have unique physical properties as well, such as a low density, low melting point, and it being soft and being able to be cut with a knife. Here are the reactions that alkali metals undertake with water, and they follow the general format of that highlighted in brown. Looking at this equation, which involves rubidium in water, are you able to tell which is a reducing agent? The answer is rubidium, as the oxidation state of rubidium increase from 0 in rubidium to +1 in rubidium hydroxide. Therefore, generally all group 1 metals are powerful reducing agents. Down the group, the reactivity of alkali metals in water increases as rubidium reacts violently and explosively, while potassium reacts explosively, and lastly sodium only reacts vigorously. Sodium and potassium have density that is less than water, while from potassium to rubidium, since there is a significant jump in AR, rubidium is now more dense than water, and therefore only rubidium sinks in water. The diagram below shows the color of flames that are produced when respective alkali metals are burnt in it. Group 7 halogens. Halogens are highly reactive nonmetals, and are diatomic molecules. Most of them are colored and form colored compounds, and since they have covalent bonds, they have a low melting and boiling points, and do not conduct electricity. Down group 7, the melting point increases, the reactivity decreases, and the density increases as well. Since the atomic radius of group 7 elements increases, it makes it more difficult for elements to take in or share electrons, therefore the element is less reactive. Since melting or boiling point represents the strength of the intermolecular forces between covalent molecules, the larger the covalent molecules, the stronger the intermolecular force, and thus the higher the melting or boiling point. In summary, down the group, there is an increasing melting point, as the covalent molecule is larger, and therefore establishes stronger intermolecular forces. The reactivity decreases as since atomic radius increases, it makes it more difficult to pull in electrons. Lastly, the density increases, as the mass number increases. For the reaction between potassium bromide and chlorine, it is exhibited in the equation below, and the color changes that of colorless to orange since liquid bromine is being produced. For the reaction between potassium iodide and chlorine, it is seen in the equation below, and the color goes from colorless to that of a brown solution as the complex iodide 3- is formed. For each of the halides seen below, when acidified silver nitrate is added to them, precipitates of different color will be formed as stated. In summary, for halogens their color darkens down the group from yellowish in fluorine and chlorine, to brown in bromine, and lastly to black in iodide. Group 0 noble gas. Noble gases are unreactive and monoatomic with 2 or 8 electrons in its outermost electron shell. They also have low melting and boiling point, and thus are a gas at RTP. They are also colorless, and down the group, the melting and boiling point increases. Helium, which is a noble gas, is used for filling balloons due to its low density. And on the other hand, argon is used to fill light bulbs, and are largely unreactive and protects the white hot filament from vaporizing, and argon is also cheap due to its abundance. Transition metals. Transition metals have more delocalized electrons than that of other metals, and thus have better conductivity and conduct electricity better than alkali metals. They also have higher melting and boiling point than that of normal metals, as they have metallic bonds, and lastly, they have a higher density than most metals. They also have variable valency, and hence form colored compounds, and can also act as effective catalysts. An example of a transition metal is that of iron. Below shows the several color that iron compounds can take. Another transition metal is that of copper, with copper 2+ having a blue color, and the complexes of copper formed have several shades as seen in the diagram below. When it comes to chromium, it forms several ions with each one taking on a different color as stated below and seen in the diagrams on the side. Lastly, vanadium forms various complexes well as stated below and seen in the diagram. In summary, down group 0, stronger intermolecular bonds are formed, therefore there is an increased melting and boiling point, and secondly, since the mass number increases, the density increases as well. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.